Right, this is Module 4, Lecture Notes 8. You will need your periodic table for this set of lecture notes, so if you want to grab that and something to write with, I think we'll be all set. All right, so in this lecture, we're going to start talking about how atoms and molecules behave when they react with each other. Now that we know the difference between atoms and molecules, we can start seeing how they're going to interact in different combinations. One of the things that your book talked about as you did your pre-reading is something called the kinetic theory of matter. And I want you to focus on that word kinetic for a second. Remember in Module 2, we were talking about different kinds of energy. We talked about potential energy and kinetic energy. And if you remember, kinetic energy is the energy of motion. Okay, potential was stored. Kinetic is the energy of motion. So this kinetic theory of matter tells us that molecules or atoms that make up all matter are always in constant motion. Okay, so what that's really saying is the atoms that make up matter, or everything around us, are actually moving. Okay, so we know there's atoms inside my pen. There's atoms that are making up that plastic. If we could see those atoms on a very, very small scale, if we could zoom in and look at individual atoms, they're actually moving. That's crazy. The atoms in this paper are moving. The atoms in your hair are moving. The atoms in the air around us are moving. All the atoms are in constant motion. And I think that's pretty cool. So let's look at how the atoms move differently in the different states of matter. So let's look at solid first. Something that's solid might be a piece of ice or a book or whatever, a solid object. When you think about the atoms in a solid object, picture them in an orderly arrangement. They're orderly because they come together to form the shape of your object. Okay, so maybe they look like that. They are just vibrating back and forth in place. So just teeny tiny little vibrations in place. They have a fixed shape and a fixed volume. They do not fill the whole container. They stay in their orderly arrangement. Okay, hopefully you watched the simulation that was in your before class notes, because that gives you a really good visual of the difference in the movement between these three. A liquid, maybe water or a Coke or something like that. A liquid, the atoms are going to fill the bottom of the container. They spread out. They're not very orderly arranged. So you can picture if you poured water in here, it would fill the bottom. And these atoms slip and slide past each other. The shape can vary because the shape of the container can vary. But the volume stays the same. It's always going to fill the bottom of the container. The volume is fixed. They spread out, fill the shape of the container. And then lastly, for a gas, maybe like oxygen gas or carbon dioxide gas, when you draw a gas, you're going to show that the atoms can go anywhere within the container. They bounce off the walls, they hit each other, and they are moving all around. The shape can vary for a gas because if we would let it, if we opened this container, the gas would go into the whole room. And the volume, same thing. If given the space, the gas will fill whatever you let it. So the shape is variable and the volume is variable for a gas. One of my chemistry teachers a long time ago gave me an analogy that really stuck with me for these three. They told me to think of a classroom. Okay, when class is in session and your students are sitting in their desks, they're like a solid. They're orderly arranged. They might be shifting in their seat, but they're not moving around the room. So they're like vibrating back and forth just in their chairs. Okay. A liquid would be like the students moving around within the classroom. They're slipping and sliding past each other, turning a paper in at the front, but they're staying in that fixed classroom. And then a gas is like passing period in a big school where you're bumping into each other and bouncing off the walls, and you spread out to go to your next class. You're allowed to leave the container and fill the shape of a new classroom or a hallway or use the restroom. It's very spread out. So maybe that helps you think of those different movements in the states of matter. So why are these molecules moving? Well, the kinetic theory of matter tells us that they're in motion because they have energy. And they get this from their surroundings. Okay? Things that have a higher temperature mean they're going to move faster. And things that have a lower temperature are moving slower. So think about temperature being a direct relation to the amount of energy it has. Okay? Particles that are hot have a lot of energy, they're moving fast. Particles that are at a lower temperature are moving slower with less energy. All right, let's move on to the next section in this chapter. We're going to start looking at what happens when we combine different elements in order to react them together. Before we get into some actual reactions, one thing you need to know is that some molecules always have to have a partner. These are called diatomics. Think of the prefix di. You should think of two. These molecules are made up of two atoms, which are the same. There are 7 of them on the periodic table. Okay, I like to think of them as being lonely. They cannot be by themselves. They always have to have a partner. So what I mean by that is nitrogen cannot just be written as an N when it's in a reaction. It has to be N2, 2 nitrogens bonded together. Oxygen, chlorine, fluorine, bromine, iodine, astatine, and hydrogen. Okay, sometimes this astatine is not included. You can include it if you want. You'll see it falls into the pattern. That's pretty easy to remember. But let me show you where these are on the periodic table. They start at element 7, and they make the shape of a 7. So if you have a darker colored marker, go ahead and outline these to help you remember which elements always like to have a partner. Okay, they start at number 7, they make a 7, up, hydrogen. So my rule is 7 up. Start at 7, make a 7, and up reminds you that hydrogen is included in the upper right-hand corner. 7 up. You must memorize these 7. So hopefully that rule helps you find it and memorize it pretty easily. All right, so let's look at some chemical reactions. Remember that a chemical reaction is in which one or more substances react together to produce a new substance. So here's an example. Carbon reacts with oxygen to produce carbon dioxide. So this is a reaction that's written with words, and we can also write it with symbols. Carbon reacts with oxygen. Notice I have O2 because it's one of these special diatomics to produce carbon dioxide. The things on the left of your arrow are called reactants. They react together to produce your product. Sometimes there's one product and sometimes there's more than one. Oftentimes when you're working with chemical reactions, you will see little symbols after your elements, and these are called state symbols. They tell us what state of matter your reactants or your products are in. If you see a little S, that means it's a solid. Those are often going to be metals. Liquids, you're going to see an L. Gases, you'll see a G. And a lot of your gases are found in groups 7 and 8, right here. Fluorine, chlorine, bromine, iodine, and then all of these are going to be gases as well. And then if you see an AQ, that stands for aqueous. And that's just anything that's dissolved in water or a solution. Okay. While we're talking about chemical reactions, I want to introduce to you the concept of balancing. Chemical reactions need to be balanced, which means you need to have equal numbers of each type of element represented on both sides. And that's because of the law of conservation of mass, which we've talked about. Whatever you start off with, it can change form, but it can't disappear. It can change form, but its mass is always conserved. So we have to have the same number of each element on both sides. Okay? Your reaction can be divided down the middle of your arrow. Reactants and products. You're going to see numbers, these are called coefficients, out in front of your reactants and products. This coefficient goes to the carbon and to the hydrogen. This coefficient goes to the oxygen. Okay, so let's look at this equation here and ask ourselves, is it balanced? So I want you to draw a line down the middle. We're going to list out the elements. We have hydrogen, chlorine, calcium, and bromine. And we have those same elements on the other side. Let's count them up and see if we have the same number of each element on both sides. If we do, then our reaction is balanced. So let's start with hydrogen. Here I have 2H. So I have 2 hydrogens. What about on the products? 2H. Let's go to chlorine. Remember, this coefficient goes to the hydrogen and to the chlorine. Here I have 2 Cl2s. So how many chlorines do I have? 2 times 2 means I have 4. Calcium, there's nothing in front of it, so I assume I just have 1. And on this side I have 2. Bromine, Br2, and 2 Br. So if I'm looking at my numbers here, it looks like my chlorines are not the same. This reaction is not balanced. So if you encounter that, you need to balance the reaction. So let me show you what that would look like. If we look at this first example here, I'm going to start with nitrogen. I see I have N2, or 2 nitrogens, and over here I only have 1. So in order to make 2 of them, I need to put a 2 out in front. Oh, well, look what that did to my hydrogens. Now I have 2 times 3. I have 6 of them on the product side. 3 times 2 will give me 6 on the reactants. And then I fill in a 1 for what's left. Okay, so balancing reactions, you just start with something and try to make that element balance. Then go to the next element, and when you finish, all of your elements should be balanced on the left and the right. I'd like you to take a second to try this one on your own. Okay, so this is the reaction of the formation of water. Hydrogen and oxygen make water. I have 2 hydrogens on the left, 2 hydrogens on the right, so I'm just going to leave it for now. When I look at my oxygens, I have O2, so this will have to be 2O. Doing that upped my hydrogens to 4. So I'll have to go back and add a 2. 2 times 2 makes 4 on the left, 4 on the right. I think I'm good. All right, let's look at a reaction in which you have to take the words and form the symbols and balance it. So that's kind of putting everything together that we've talked about in today's module. This is propane gas, like propane you use on your grill. Propane reacts with oxygen. You think it's okay like that? Oxygen is actually one of the 7 that we talked about. It can never be alone. It always has to be a diatomic. Propane reacts with oxygen to make carbon dioxide, carbon dioxide, and water. I like to put little lines here for my coefficients. And let's do some balancing. I'm just going to start here with carbon. I have 3 on the reactant side, so I need to put a 3 here on the product side to make 3 carbon. Let's move to hydrogen. H8. What times 2 is going to give me 8? All right, now I need to figure out my oxygens. Whoa, I've created quite a few over here. I have some with my carbon dioxide and some with my water. So let's step through this one together. I have 3 times 2 oxygens. So I have 6 from my carbon dioxide plus 4 O's from my water. I have 10 oxygen on the product side. So I know my coefficient needs to be something times 2 to give me 10. Perfect. And then I'm going to put a 1 here. It's always good to go back and check each element again. Make sure you have the same on the reactants as you do on the products. All right, I'd like you to take a second to write out this reaction and begin balance. Calcium and oxygen react with carbon. This and carbon make calcium carbonate. So I didn't give you the formulas for these because I think by this point you can write the symbols for these things that we've talked about. Calcium carbonate, I don't expect you to know, and in that case on a homework or a quiz or a test, you would always be given that sort of formula. All right, now we're up to the task of balancing. So I always just start with the first element most of the time. Calcium, 1, 1, I'm gonna leave it. Oxygen, I have 2 here and 3 here. What you will learn in a lot of these problems is that when you have 2 of something and 3 of something, you're gonna need to take them both to 6. 3 times 2, 2 times 3. Now I have 6 on each side. But putting a 2 here changed my calciums. And it changed the carbons. Now I have 2 carbons. So I need 2 carbons. That should work that out for the balancing of that one. Okay, you'll see at the bottom of the paper I've written practice, practice, practice. These will get so much easier with practice. By Module 5, balancing is going to be something that you need to be pretty good at. So please do your homework, practice problems in your book. If your teachers give you extra practice, definitely do it. And if you're having trouble with it, this is the time to ask for help so that when we build on it, you don't get behind. Balancing is a really, really important skill, and you will get the hang of it with practice. Okay? Thanks for listening.